Hello, so in this video we're going to start looking at the next theme, which is probability. Now, we're not going to go into probability too much in this video, even though we are starting the next theme, but I just wanted to give you an overview of what probability is, and then that will explain a little bit more about why we're going to look at what we're going to look at today. So probability is all about the maths of chance. Okay, probability is kind of really useful in everyday life. It's all to do with calculating risk. Okay, so making decisions, we use risk to determine whether we should do a particular thing or not. Okay, so probability all helps us how to work out the maths of chance, how to work out chances or risk of things happening. Now, the theoretical way of calculating a probability. So if you want to calculate the probability of something happening, now the something happening we call an event, and we want to work out the probability of this event. So you see the notation I'm using here, the P stands for probability, then in brackets I have the event. So the way to work out the probability of something happening, the theoretical probability, it should be the number of outcomes of interest, okay? So the number of outcomes of interest to us, okay? Divided by the total number of outcomes that can happen. And we call that the sample space. So the sample space is every single possible outcome that can happen, the number of different possible outcomes that could happen. Okay. So for example, if you want to work out, if you have a fair coin, okay, and you want to work out the probability of getting a heads on this coin, assuming of course it's fair, okay? Well, the number of outcomes we're interested in the heads, okay? Well, how many heads are there on a coin? There's one, okay? The sample space is the total number of things that can happen. So let's think, on a coin, you've either got heads or you've got a tails. There's two things that can happen there. So therefore, the theoretical probability of getting a heads on a fair coin should be a half. In other words, half the time you should get a heads, okay? Now you notice that the very definition of how we calculate probability, this thing in blue, okay, the very definition of how we calculate the probability, it requires a way of understanding how many things are likely to happen. So it needs a way of counting the number of different possible outcomes, okay, either for the outcomes of interest or for the sample space, okay. So what we're going to start looking at today is this idea of counting, okay? How can we possibly work out how many different possible outcomes there are, okay? And this is coming into this idea of ordering and counting, otherwise known as permutations and combinations, okay? Or perms and coms for short. Okay, and literally what we're going to look at in today's video is simply how many different possible ways are there of choosing objects or ordering objects or just simply working out the number of different ways of counting objects, okay? And this is called permutations and combinations. So let me start you off with an example here then, okay? So let's suppose we have a lock. Okay, and it's a 4-position lock, so you can basically see on each of these wheels there are 4 different possible wheels, and on each wheel there's 10 digits, so the digits 0 to 9. Now in each of these positions, on each of these wheels, there's only one digit that's correct. There's only one digit on each of these wheels, which just, when all the wheels are correct, the lock will open. And my question is, how many different possible orderings can we have? Now I want you to pause the video for a second, just have a think and think, how would I work this out? Okay, so hopefully you've had a chance to pause the video. Now, if I'm working with this problem, and if I'm seeing this problem for the first time, I think the key is I need to simplify it. And if we can simplify it and understand what's happening in a simpler case, then hopefully we can extend it to a more complicated case like this. So let's actually just look at a slightly different type of lock. Same kind of principle. So you've got wheels, and only one digit in each of the positions are correct, and that will open the lock. But this time it's only 2 wheels, and on each wheel you only have 5 digits. Okay, so position 1, position 2, and there's only 5 digits which you can choose from in each position. So the digits 0 to 4, let's say, and again, only 1 digit per position is correct. Well, I think because it's a slightly simpler example, there's only 2 wheels, there's only 2 positions, and there's only now 5 digits in each of the wheels, in each of the positions, I think we can actually draw out every single possible outcome, okay? So I'm going to do so using a table like this. So the rows of the table represent the digit which can be displayed in that first position. And the columns of the table represent the digit that can be displayed in the second position. And obviously I've listed the only 5 possible digits that you can have in each position are the digits from 0 to 4. Okay, there's 5. 1, 2, 3, 4, 5. So 0 to 4. Okay, and that's the same in each position. So basically, if I choose to put a 0 in the first position, would you be happy then? There's still 5 choices that I can have in the second position. I can either have a 0, a 1, a 2, a 3 and a 4. And you can see I've represented those choices with a dot. So this dot here, for example, means that I choose a 0 in the first position and a 0 in the second position. The next dot along would represent a 0 in the first position and a 1 in the second position. Next dot along would be 0 in the first position, 2 in the second position, etc, etc, etc. So would you be happy if I chose a 0 in the first position? There are 5 choices to go in the second position. All right, now what happens if I choose a 1 in the first position? Well, are you happy? There's still 5 choices for the digits in the second position. So if I choose a 1 in the first position, I can have a 0 in the second, or a 1 in the second, or a 2 in the second, or 3 in the second, or a 4 in the second. And so on and so on and so on. So if I choose a 2 in the first position, again, there are still 5 choices for what happens in the second position. And the same with the 3 and the same with the 4. So in total, because there are 5 rows or options for position 1, and for each of those options that I choose in position 1, so whether I choose a 0, whether I choose a 1, a 2, or 3 or 4 for position 1, there will always be 5 choices for what I choose to put in position 2. Okay, so therefore there are 5 columns or options for position 2. So in total then, the total number of options, remember each dot in the table represents an option, in total number of options are, well, 25, okay? So there are 25 different possible orderings I can have with a 2-position lock where there's 5 digits on each of the wheels, on each of the positions. So now if I extend that back to the original problem, that exact same idea, well, remember, instead of having 2 positions, having 2 wheels, we've now got, well, 4 positions or 4 wheels, okay? And now instead of having 5 digits on each wheel, we've got 10 digits on each wheel. But the principle is still the same. So basically, in the first position, I can choose 10 different possible options. In the second position, I have 10 different possible options. Third position, I have 10 options. And in the fourth position, I have 10 options. So what should I do with these 4 numbers? Well, I've just seen in the last example that I can represent that. If I do it on a sort of a table, it means that I have to multiply these numbers together. It's literally rows by columns, okay? Well, in this case, I need to do 10 by 10, and then I need to times each of those options by another 10, then each of those options by another 10 to represent the 10 different possible options in each position. So therefore, if I multiply all these together, that will give me 10,000 possible options which go in each position. Okay, so the answer is, how many different possible orderings, how many different ways can I choose a combination for this lock? There's 10,000 different possible ways. So just to kind of give you a bit of an appreciation of what's going on here, okay, I've actually got 2 locks here. So let's suppose I walk into a shop and I see 2 locks in front of me, okay? I see one lock which only has 3 positions, but there's 10 digits which can go in each position. And there's another lock right by the side of it which has 4 wheels, 4 positions, and again 10 digits can go in each position. So you think, well, hang on a minute, like this lock, lock A, and this lock, lock B, there's not really much difference, there's just an extra wheel. So my question is, well, how much more secure is the second lock than the first lock? Are you happy it has to be more secure because there's an extra wheel, okay, so there's an extra kind of option that you have to have, so the second lock will be more secure. But my question is, how much more secure? So, I mean, you might be looking at this intuitively and thinking, well, hang on a minute, I've only added an extra wheel, like, I can't have made it that much more secure, surely. So, I'm going to ask you the question, can you tell me how long each lock will take if I'm going to try every single possible ordering? So let's imagine a thief comes along and you're going to try every single possible ordering of each lock. Okay, and you're going to try a different order every single second. So 1 second, try order. Second, try a different order. Next second, try a different order. And you're going to try a different order every single second. My question is, how long will each lock take to try every single possible ordering? Let's imagine this thief is just doing a brute force approach. They are literally just going to try every single possible order and then just hope that they get the right one eventually. If you're going to try every single possible ordering, how long will each lock take? Well, if you look at lock A, we've just established that it's going to have 1,000 different possible orderings. You happy? Because there's 10 digits in each position and there are 3 positions. So it's going to be 10 times 10 times 10, which is 1,000 different possible orderings. Now you could say, well, that takes 1,000 seconds. But I think to give a more meaningful representation of this data, 1,000 seconds you can think of, if you divide by 60, as 16 minutes and 42 seconds. Okay, 16 minutes and 42 seconds, right? Now, if you do the same for lock B, well, we've just established there's 10,000 different possible orderings for lock B. So what's 10,000 seconds? Well, it's 166.7 minutes. And you divide that by 60 again, you get 2 hours, 42 minutes, okay? So in other words, if you look at these two locks, okay? Lock A, where you just have 3 wheels, right? Well, it will take about 16 minutes and 42 seconds. So just around 15 minutes to crack every single possible combination. Whereas you look at lock B, just by having that extra wheel on there, that's the only difference, just got an extra wheel on there, it's going to take nearly 3 hours to try different possible orderings. So this is a really important point that I do want to emphasize here. You think just by adding that extra kind of option, that extra sort of order, that extra wheel, that extra position, you think it's not going to make it that much more secure, but look at the difference, right? The first lock with 3 positions, you can crack in about 15 minutes. The second lock with 4 positions, just that extra wheel, is going to be there for nearly 3 hours. And you hope by that time, somebody will notice that something's going on, or the thief might get bored and hopefully give up. Okay. So another kind of example of this, kind of counting orderings. Let's suppose you walk into a coffee shop. All right. And this is the kind of menu behind the baristas of the coffee shop. Okay, and you can see you basically have to select a coffee, so whether you want a latte, an espresso, a cappuccino or an Americano. You then have an option for the size, so you can either have a small, a medium and large of each of the coffee that you select, and then you can also add a syrup, and there's 5 different possible syrups: caramel, chocolate, vanilla, hazelnut and honey. My question is, how many different possible orders can you have? So how many different possible ways are there of ordering a coffee? Now, of course, assume that you have to choose one type, you have to choose one size, and you have to have a syrup. So you have to choose one of each. So a type, a size, and a syrup. How many different possible orderings are there? So pause the video, have a think, okay? And then we will come back and have a think and have a decide. Okay, so hopefully you've had a chance to have a think. So let's have a look at this then. Okay, so we basically have to choose a type, a size, and a syrup. Well, how many different types of coffee were there? Well, there was a latte, an espresso, a cappuccino, and an Americano. That means there were 4 different types of coffee, okay, which you could choose from. Then you think, how many sizes were there? So we had to choose either a small, a medium, or a large. There's 3 types of sizes. Okay, so there's 3 sizes there. Then how many syrups? Well, there was caramel, chocolate, vanilla, hazelnut, honey. That gives me 5 different options for syrups. So therefore, given that I have to choose at least one of each of these, so I have to choose a type, a size, and a syrup, I should just multiply these numbers together. So 4 times 3 times 5. That should give me 60 different possible coffees that I could order from this shop. Okay, so 60 different possible ways of making a different order. Okay, so similar kind of thing then, let's have a look at this example. Okay, so let's suppose we have a sandwich, okay? And you've probably seen these kinds of menus before. So you need to order a sandwich, you need to choose a bread, a filling, veg, cheese, and then sauce. And you have to choose one of each, okay? So with no skipping. If you don't want the veg, you have to choose a veg, all right? So you have to choose one bread, one filling, one veg, what type of cheese you want, so either melted or cool, and then one sauce as well, okay? So how many different possible ways are there of making an order in this shop? All right, okay, so hopefully you've had a chance to have a think about that. Let's have a look at this, okay? So the bread, the filling, the veg, the cheese, and the sauce. So how many different types of bread were there? Well, basically, there was... You could either have Italian, oat, spicy, cheese, rosemary, rye, or gluten. So there's 1, 2, 3, 4, 5, 6. There's 7 different types of bread that you could have. Okay, then how many different types of fillings? Well, you could either have vegan, veggie, chicken, ham, meatball, or tuna. That gives me 6 different possible fillings. Okay, how many different types of veg were there? Well, there was cucumbers, peppers, onions, tomatoes, olives, pickles, lettuce, or sweet corn. It's 1, 2, 3, 4, 5, 6, 7. There's 8 different types of veg that you could have. And then for cheese, well, you can either have melted or cool. So there's 2 different types of cheese. And then for sauce, you could either have ranch, mayonnaise, barbecue, ketchup, or oil. That gives me 5 different types of sauce that I could have. So therefore my job now is just to multiply all of these numbers together. I'm going to reach for the calculator just because I'm feeling fairly lazy today. Okay, so I'm just going to stick 7 times 6 times 8 times 2 times 5, and that should give me 3,360 different ways of making my order in this sandwich shop. Okay, so it's 3,360 different ways. But hopefully you kind of get the idea here. The idea of this is that effectively I'm just multiplying together all of the different options that I could have. Okay, and the reason being is because I have to choose one of each. Okay, so if I choose a bread, there's 7 different possible breads that I could choose. Okay, and then for each of those 7 different possible breads, there's then another 6 different possible fillings. And then for each of those choices of bread and fillings, there's another 8 different possible choices of veg, and so on and so on. Hence the reason why you have to multiply. Okay, effectively I could draw out a really big table to kind of accommodate all of my choices, but it would just end up that I just end up multiplying everything together anyway. Okay, so let's have a look at the next example. So this is a slightly different example. Let's suppose I have 3 different people standing in a line. So a pink person, a black person, and a blue person. So 3 people standing in a line. My question is, how many different possible ways are there of ordering these 3 people in a line? Okay, well, let's think about it like this. Hopefully you realize that there's 3 different possible positions. Okay, so here's my 3 people. I've got this person, I've got this person, and I've got this person. Okay, so I've got these 3 people standing in a line. Okay, and are you happy that there's 3 different possible positions to put them in? So 3 positions. So there, and there. I basically just need to choose how many different options can go in each position. So let's have a look, shall we? Okay, so here I have just by brute force, I've written out drawn out all of the different possible options. Okay, so you can either have the pink person first, and the black person, and the blue person, or you could have the pink person first, and the blue person, and the black person, etc, etc, etc. So I could just draw out, just by brute force method, all of the different possible orderings that I have. In this case, there's only 3 people, and there's going to be 6 possible orderings that I can have. However, the brute force method is fine, and I'd encourage you to do it if you're really not sure where else to go. But it's going to take quite a long time, particularly if I add more people. Okay, we've just seen with the lock example that just by adding an extra lock, just by adding an extra position, it suddenly becomes like massively bigger. Okay, so if I add an extra person in here, don't think that it's just going to be a couple more kind of orderings which I add on here. It's probably going to be more like, well, in fact, I know it's going to be more like 18 different more possible orderings, so 3 times as many. Okay, so yeah, so if you add an extra person, it's going to take a long time to draw every single possible ordering out. But that's okay, because if we can spot the pattern, then we can generalize, and then we can know what to do in the future. So here we go. Let's suppose I've got my 3 people. So I've got my 3 people down here at the bottom of my screen, and I've basically just drawn out the 3 possible positions that these 3 people can go in. So my question is, let's start from left to right. How many people can we choose from to go in that first position? Well, are you happy that we haven't chosen anyone yet? So all 3 people are fair game to go in that first position. So we've basically got to choose from 3 different people. Okay, so let's just put him in there. Okay, it doesn't matter who we put in there, but let's just put someone in there. All right. So now let's have a look at position 2. That's the next position to fill, right? Well, how many people are left to choose from to put in position 2? We've just seen, because you've chosen someone to put in position 1, there's going to be 2 people left to choose from to put in position 2. They may not be the black and the blue person, it may be the pink and the blue person if you chose to put the black person in the first position. But my point is, there's always going to be 2 people left to choose from to put in the second position, because you've already chosen someone in the first position. So in other words, you've got 2 people left to choose from. All right, well, let's just put the black person in there then. Okay, so we put the black person in position 2. Well, then finally, if we come on to the third position, how many people have we got left to choose from to put in the third position? Well, because we've already chosen someone to put in position 1, and because we've already chosen someone else to put in position 2, that means that there's only going to be 1 person left sitting over here. Now, again, I've just given an example here where the pink person is chosen first, and then the black person is chosen second, which leaves the blue person last. But my point is, if you generalize this to a different case, if you chose to put the blue person first, then the pink person second, my point is there's always only ever going to be 1 person sitting here once you've chosen 2 people to put in the first 2 positions. So in other words, you've got 1 person left to choose from. Okay, so obviously they have to go there. Okay, so my point is, when you generalize this, there's 3 different people that go in first position, 2 different people left to choose from to go in the second position, and 1 person left to choose from to go in that last position. So therefore, if you multiply these numbers together, use exactly the same technique as we were using in the previous example with the locks and with the Subway sandwiches and with the coffee example, you should just multiply the different possible options that can go into each position. So therefore, there will be 6 different ways of ordering this line, and that corresponds to exactly the same thing we saw there. We actually drew out those 6 different possible positions, okay? But this is a more general way of doing it, okay? Now notice here that I've used a different word. I've used permutations. That is a word that we will come across more and more. It literally just means an order, okay? So another word for an ordering is a permutation, and we will use that a little bit more, all right? Okay, so now let's just generalize it then. What if we had 4 people standing in a line? Now, like I say, you could draw them all out, but there's going to be 24 different possible options. It's going to take quite a long time. And obviously, the more options you have, the more careful you have to be. And you have to kind of come up with your own little system to make sure that you don't miss any, okay? But that's fine, because actually we can just generalize what we saw in the last slide to see what happens with 4 people. So in this case, there's going to be 4 different possible positions, okay? In the first position, there's going to be 4 different possible people. In the second position, there's going to be 3 people left to choose from. In the third position, there will be 2 people left to choose from. And in the last position, there will only be 1 person left to choose from. So therefore, if you multiply the 4 by the 3, by the 2, by the 1, you get yourself 24 different possible permutations. Remember, permutations just means an ordering. So there are 24 ways of ordering these 4 people into a line. So let's have a look at this in general. Let's start to notice a pattern and see if we can generalize this. Well, if we just got 1 person that we need to order, well, happily there's only 1 person to choose from, so therefore there's only 1 way of ordering this person, okay? If there's 2 people in a line, well, there's 2 people that you can choose from to put in the first position, and then 1 person to choose from to go in the next position. So therefore, when you multiply them together, you get 2 times 1. Now, we've just seen with 3 people, you get 3 times 2 times 1, and with 4 people, you get 4 times 3 times 2 times 1. Now, you notice the pattern here, okay? How many different ways are there of ordering the objects, okay? Well, if you have 1 object, it's just 1. If you have 2 objects, it's 2 times 1. If you have 3 objects, it's 3 times 2 times 1. 4 objects, 4 times 3 times 2 times 1. 5 objects would be 5 times 4 times 3 times 2 times 1. 6 would be 6 times 5 times 4 times 3 times 2 times 1. This kind of pattern will carry on regardless of how many objects you have. So in general, n objects will just be n multiplied by the n minus 1 times n minus 2, etc, 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 all the way down. So you're just basically multiplying by the consecutive numbers. You start at the number of objects you've got. In the last example, we had 4 objects. Then you multiply that by consecutive numbers, so 4 times 3 times 2 times 1. Now, because this is such a key and central idea, we actually give this notation. So we want to give this its own special notation because it's literally talking about the number of different ways to order n objects into a line. Okay, and so therefore we call it a factorial notation. And you notice it just has this exclamation mark after the number. Okay, so if you look at the last example, there are 4 objects. So 4 times 3 times 2 times 1, that would be 4 factorial. So 4 with an exclamation mark after it. Okay, doesn't mean 4, like shouting out, it just means 4 factorial. Okay, and that just simply means multiply by the consecutive numbers after 4, and 3 factorial, and 2 factorial, and 1 factorial. Okay, so in general then, the number of different ways of ordering n objects into a line would be n times n minus 1 times n minus 2 times n minus 3, right the way down to 4 times 3 times 2 times 1, or just simply n factorial. So maybe you might want to pause the screen and have a go at these 3 questions here. Okay, they shouldn't be that difficult, but they should be fairly obvious. Okay. All right, so now let's actually have a look and see what happens if we have a few conditions. Okay, so let's suppose I have the letters cook, C-O-O-K, and I want to work out how many different ways can I arrange these letters in a line. Okay, well, you look here and you say, hang on a minute, there's 4 different letters. Well, I've just seen in the last few slides that if I have n objects, the way to order them, the number of different orderings for those, would be n factorial. So if I've got 4 letters, it makes sense that the number of different letters, the number of different orderings, rather, for these 4 letters should be 4 factorial. Is that strictly true though? Well, let's see. If I flip around those 2 O's, so you've just seen I've just flipped those 2 O's around, do I actually see any difference in the letters I have on the screen? So let me show you that again. Let's suppose I start off with these 4 letters, C, O, O, K, and then let's suppose if I switch those 2 O's around. So there you go. Do you see any difference? If I didn't tell you I've switched those 2 O's around, would you be able to tell? And the answer is no, okay? So actually in this case, we need to be a little bit more careful. It's not just quite as straightforward as just 4 factorial for the number of different arrangements, okay? So because they're no longer distinct objects, distinct is the key word there. Distinct means different. Because the C, the O, and the K are no longer all distinct, i.e. the 2 O's, they look the same to me, okay? They're no longer distinct, therefore we need to be a little bit more careful. So if I actually draw out all of the different possible permutations where I don't consider the O's as different letters, so I don't consider the O's as the same letter, then this is what I would get. So basically if I just drew out all of the different possible permutations, and let's suppose I tell you that I've switched the 2 O's around, these would be all of the 4 factorial permutations, or the 24 permutations, okay? And you see the top 2 examples, even though they look to you exactly the same, they're not the same. The reason being is because I've switched the 2 O's around. And with the next 2, okay, there's row 2, I've switched the 2 O's around to get from the left column to the right column, okay? So in other words, all of the column on the right are all indistinguishable. I cannot tell you that the reason I cannot tell you they're different because the 2 O's are the same. I've just simply switched them around and they look exactly the same as the ones in the left column, okay? So what I need to do instead is I need to think about the number of different ways of arranging these 2 O's in a line. Okay, well, are you happy if I've got 2 objects and I need to work out the number of different ways of arranging them in a line? There's just going to be 2 factorial different possible arrangements. Okay, so in other words, these 2 O's, when I switch them around, just like I do with everything in this right column, to get from left column to right column, just switch the 2 O's around. In other words, there's 2 factorial ways of arranging these 2 O's. In other words, these arrangements will be repeated that 2 factorial times, just to represent the O's being flipped over, okay? In other words, I need to remove them from my original 4 factorial that I thought. So here's my 4 factorial arrangements. I need to remove all of the repeated arrangements. And I've just seen that the repeated arrangements will come when I switch the 2 O's over. So in other words, the 2 factorial ways of arranging those, okay? So just think. Given that a factorial is all to do with multiplication, think 4 factorial means 4 times 3 times 2 times 1. If I need to remove arrangements, well, what's the opposite of removing something which is being multiplied? If I want to remove something where I'm multiplying, surely I should just divide, right? Because divide is the opposite of multiplication. It's going to undo the multiplication. So if I want to remove something from a multiplication, I should divide it. Hence, I have my 4 factorial, which represents all of the different possible permutations, where I just say, do you know what? They're all different letters, I don't care, okay? And then I need to think, well, hang on a minute, the 2 O's, they can switch over, so there's 2 factorial different arrangements of those, so therefore I need to remove them by dividing, okay? So there we go. So in total, I will be left with 12 distinct permutations. So this is really important. If you have repeated objects, and if you have repeated objects, you just need to consider, well, okay, in total there are 4 letters, fine, so there's 4 factorial different permutations. However, 2 factorial of those, because there's 2 factorial ways of arranging the O's, are going to result in repeated orderings, okay, repeated arrangements. So therefore I need to remove them, and I remove them by dividing. Okay, so maybe you might want to have a go at these. So this is in general. If you have n objects which you want to order, that's n factorial. But if you have A or B or C, that's going to be the number of non-distinct objects which you have. Okay, so A, B, and C, that's the number of non-distinct objects that you have. Okay, so for example, in this first one with tweet, we can actually probably go through this. Okay, so with the word tweet, how many different possible distinct orderings can I have? Well, ordinarily you would say, well, hang on a minute, there's 5 different letters there, so surely it should be 5 factorial ways of arranging these 5 letters in a line. However, okay, we have 2 T's, which means if I flip these 2 T's around, okay, you're not going to notice. So I need to remove the number of different repeated arrangements for my T's. So I need to divide by 2 factorial because there are 2 factorial ways of arranging my T's in each of these 5 factorial different arrangements. However, you also notice that I have 2 E's, which means if I flip those 2 E's around, you're also not going to notice a distinct arrangement. So therefore, I need to divide by another 2 factorial to represent the fact that I have 2 E's. Okay, so the first 2 factorial is because I have 2 T's. And the next 2 factorial is because I have 2 e's. Okay? All right, let's have a look at the next example then. Let's have a look at statistics. Okay, so how many distinct permutations exist of the word statistics? Well, let's have a look. If I write the word statistics out, like so. Well, how many different letters, or how many letters are there in total? Okay, well, okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different letters. Okay, 10 different letters here. So therefore, in general, or usually, there'd be 10 factorial ways of arranging these 10 letters in a line. Okay, the S, the T, the A, to T, I, the S, the T, the I, the C, and the S. Okay, however, we've got some repeated letters going on. Have a look. I've got 3 S's, which means if I swap the order of these 3 S's around, you're not going to notice the difference in these 10 factorial different arrangements. So therefore, I need to remove them. So I need to divide by 3 factorial to represent the fact that I have 3 S's. And if I swap those orders around, if I swap them all around, you're not going to notice a difference. Likewise, I have 3 T's. Okay, I have 3 T's, which means if I swap the order of these 3 T's around, you're also not going to notice. So I need to remove them from my count. Okay, so this represents the 3 T's. Okay, I also have 2 I's. Okay, I also have 2 I's, which means if I swap these 2 I's around, you're not going to notice the difference. So therefore, I need to remove them from my count again. Okay, so I need to divide by another 2 factorial to represent the 2 I's. Okay, so this is in general how to calculate the number of different distinct arrangements where you have repeated objects. Okay, you first of all just say, well, hang on a minute, there's that many objects. So in this case, there's 10 letters. So ordinarily, it would be 10 factorial ways of arranging these 10 letters in a line. However, in this case, because we have repeated objects, I need to remove the number of different ways of ordering those repeated objects so that I don't overcount them. Remember, if I switch those S's around, you're not going to notice a difference. If I switch the T's around, you're not going to notice a difference. If I switch the I's around, you're not going to notice a difference. Hence, I need to remove them from my count. Okay? All right, let's have another look at an example with a condition. So let's suppose I have Alex. I have the letters A, L, E, and X. Okay? And I want it to be, so I want to work out the number of different arrangements that there are. Sorry, I went slightly ahead there. I want to work out the number of different arrangements that there are such that the A and the E is together. In other words, the 2 vowels are always next to each other. Well, what I'm going to do first of all is just write it out so that the A and the E go together. So I'm just going to swap the A and the L, the E and the L round. And then what I want to do, because I always want the A and the E together, I'm actually going to imagine them glued together. I'm going to imagine they are glued, they're fixed, they cannot move. In other words, I'm going to treat them as one letter. So the A and the E now is one letter. So now what I'm left with are 3 letters, okay? And the number of different ways of arranging those 3 letters or those 3 objects would be 3 factorial different permutations. However, okay, for each of these different permutations, and I've written them down here, such that the A and the E glue together, for each of these, I could also have it such that the A and the E would be the other way round. Okay, so you notice all of these permutations, the A comes first and the E comes second. Okay, but I could also have it that the E and the A comes round. You notice in the question, it doesn't specify the order in which the vowels have to come. So in that case then, I need to work out the number of different permutations of my little subgroup, my little glued group together, my A and my E. So the A and the E could be either way round, therefore there are 2 factorial permutations of A and E. Okay, so here they are with the other way round. So what am I going to do then? Well, I've got 3 factorial different permutations where the A and the E glue together. But now I've also got another 2 factorial permutations to include, because the A and the E could be the other way round. Okay, so I've just seen in the last example that if I want to remove a kind of count from my orderings, okay, I should divide because I'm dealing with a factorial. So to undo a to undo a multiplication, I should divide. Now I want to include it. Okay, so in this case, because it's all to do with factorials, okay, and I'm multiplying, in order to include something, I need to multiply. Okay, so in other words, the 3 factorial represents the fact that I've glued together the A and the E. There's now only 3 objects left to arrange. However, for each of these arrangements, I have another 2 factorial ways because I could also have the A and the E round the other way. So the 2 factorial comes from the fact that I could flip the order of the A and the E. So I need to think about all the different permutations of the A and the E. So that gives me 12 different permutations. Okay, so you might want to have a go at some of these questions here. Okay. All right, fine. Now let's actually have a look at something a little bit more interesting then. So let's actually get properly into the kind of the details of what we need to do here. So let's consider this example. Let's consider that a society needs to elect a president, a vice president and a treasurer from its members. So there are 3 different possible positions: the president, then the vice president, then the treasurer. And there are 15 members in total which they need to elect from. Now my question is, how many permutations, remember permutation just means an order, how many different orderings can be formed from its 15 members? In other words, how many different ways can you fill these 3 positions from 15 different members? Well, just think, there are 3 different possible positions. There's a president, there's a vice president, and then there's a treasurer, okay? And there's 15 members which we can choose from in total. So at the moment, I haven't filled any of these positions, okay? I have not filled any of these positions. So therefore, how many different members can we choose from to become president? Well, would you be happy? Here's my 15 members over here. There are 15 different possible members to choose from to go in the president's position, because we haven't chosen anybody yet. Okay, so there's 15 people that can go there. So let's just choose someone. Let's suppose the pink person goes in there. Now let's have a look at the vice president's position. Okay, so this is the next position. How many different members are now left to choose from to go in the vice president's position? Well, are you happy? There's 14. Like, here we go, because one's already chosen to become president, which means there's 14 left to choose from to become vice president. So let's just choose someone to go in there. Fantastic. Now let's come on to the treasurer's position. Well, how many different members can we choose from to go in the treasurer's position? Well, we've already chosen 2 members, which means there's 13 left to go in the treasurer's position. Okay, so let's just choose someone at random to go in there. Okay, so in total then, to work out the number of different permutations that we can perform from its 15 members, remember what we're doing here is we're choosing 15 members, or we've got 15 members, and we're choosing 3 of them, and we're ordering them into each of the different positions. Okay, so we have 15 people that can go in the first position, 14 that can go in the second, and 13 that can go in the third. Therefore, same thing as before, we just need to multiply them. That gives us 2,730 different possible ways of electing these 3 people from 15 members. Okay, so let's actually dig into this in a little bit more detail, okay, because it's slightly subtly different to what we were doing before. If you have a look, here it kind of starts off looking like a factorial, doesn't it? So we start off with the 15 members, that's the 15 factorial that we would have done before. However, we're only electing 3 people into each position. So we're only ordering 3 of these people, okay? So it starts off looking like 15 factorial, but it doesn't finish. It doesn't go all the way down to 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8, etc., all the way down to 3 times 2 times 1, okay? It kind of cuts off. So this kind of looks like a 15 factorial. So 15 factorial would look like this. However, it's not quite. It kind of stops prematurely. It only goes as far as the 13, okay? So because we've elected those 3 people, we only want the 15 times the 14 times the 13 part of the 15 factorial. So therefore, we need to remove all of these numbers over here from the 15 factorial, the 12, the 11, the 10, the 9, the 8, the 7, etc. Okay, so therefore, in order to remove something from a factorial, what do we need to do? We need to divide. Okay, so we need to divide this kind of 12 factorial, if you like. Remember, where did this 12 come from? Well, it came from the fact that we started off with 15 members, we elected 3, which means that 12 of these people were not chosen to go in any of the positions. Okay, so that's where the 12 factorial comes from. And of course, to remove them from a factorial, we need to divide, same as before. Okay, so in other words, then they cancel off and we'll just be left with what we want. So the reason why I did this is simply because I want to relate it back to a factorial. Okay, we've just done factorials. I think we're comfortable with dealing with factorials. So I think it makes sense to relate this example, which is slightly subtly different, because we're actually not putting all 15 people into a position. We're only putting 3 of them into positions. Okay, but I want to still relate it to a factorial. So in this case, we need to remove the people that aren't chosen. Okay, so in general then, if we wanted to generalize this, we could say, well, we start off with 15 people, so there are 15 factorial ways of arranging those, but then 12 of them were not chosen. And just to show you where that 12 came from, it's 15 take away 3. It's the 15 people we started with minus the 3 people that have been chosen. We're left with 12 people that aren't chosen. And we need to remove all the different ways of arranging those people who aren't chosen to put in any position, hence the 12 factorial. Okay. Now another way of writing this, because it's a permutation, because it's an ordering, we use the P from permutation. On the left-hand side, and we kind of put it up here, we put the 15. That corresponds to the total number of objects we started with. In this case, we started with 15 members, right? And then down here, on the bottom right-hand side of the P, we put the number of members that we are choosing to put in our positions, okay? So we would read this as 15P3, 15P3. And the way we calculate it is 15 factorial over the 12 factorial, which came from the 15 minus 3 members, okay? So in general then, if we want to generalize it, the N is the number of people in our group, the R is the number of people we're choosing, and the P stands for the permutation because we're literally permuting it, we're literally putting it into an order. And the general way of calculating it is like this. So let's have a look at question 1 then. So question 1 says, a woman has 10 different rose bushes. She will plant 4 of them in a line. How many different arrangements can be made? Well, let's have a think. How many different possible things are there to start off with? How many things are in our group? Well, are you happy? There are 10 different rose bushes. So there's 10 things in our group to start off with. Okay, so there's 10 different rose bushes. So therefore, there's 10 things in our group to start off with. Okay? Then she's going to plant 4 of them. In other words, she's going to pick 4 of them out and put them in a line. Okay? So therefore, we're going to permute this because it's an ordering. Okay? How many different arrangements? Ordering. So we're going to permute this and we're going to choose 4 of them to put into a line. So it's going to be 10p4, which we can calculate as 10 factorial over, well, how many objects aren't chosen to put in a line? We need to remove all those different possible arrangements. So it'll be 10 minus 4, okay, which leaves us with the 6 rose bushes which aren't chosen to put in a line. Now, happily, you can stick all this in your calculator. If you've got a scientific calculator, the P button may be in a slightly different place, but on my calculator, it is just above the multiplication symbol, down here in the bottom left, okay? So I can just simply type 10, then bring up the P, and then I can type 4, and then press enter, and that will give me 5,040, okay? So there's 5,040 different possible ways of starting out with 10 rose bushes and then planting 4 of them in a line. Let's have a look at the next question. So how many 5-letter words, with or without meaning, can be made such that each letter can be used only once? Well, this is slightly different because it doesn't actually tell us in the question how many different things we have to choose from, the sort of starting group, if you like. But it does tell us that we're going to have to pick 4 of them out to put into a word. In other words, put them in order, okay? So let's think, how many different possible letters are there? Well, in the English alphabet, there are 26 letters, okay? So I'm going to start off with 26 possible letters to choose from. And then I'm going to pick out 5 of them and I'm going to put them in a line. So I'm going to permute them with 5 different possible letters. And again, I can stick this in my calculator or I can just simply write out the formula. So 26 factorial divided by the 26 minus 5 that weren't chosen. 26 minus 5 factorial. Okay, so let's see this. Got 26 P5. And that gives us a big number. So that's 7,893,600. Okay. Now, if we have a look at the last one, just very quickly, Alex is choosing a 4-digit PIN number. All numbers must be unique, so all the numbers in our PIN must be different. How many different PIN numbers can be formed? Well, we're working with decimal, right? How many different possible digits could we have in total? We could have 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that gives us 10 different possible digits to choose from, and we need to pick 4 of them to put in an order. Okay, so we're going to start off with 10 different possible digits. We're going to permute them because we're ordering them, and we're picking 4 of them. Okay, so it's going to be 10p4, which we can treat as 10 factorial over 10 minus 4 factorial. Well, in actual fact, that's exactly the same as the rosebush example, right? So it's still going to be 5,040. Okay, it's going to be 5,040. So there we go. Okay, if you're dealing with arrangements, but you're not dealing with arranging every single object in your group, you're only selecting some of them to put in an arrangement, then you would use a permutation. And there's the formula up there. But I think we can extend this even further, right? Because so far we've looked at orderings. There are occasions when actually you're not worried about ordering. And this is where we come into this idea of selection. Okay, so let's suppose that a teacher needs to choose 3 people from a class. And we know there are 5 class members, and I've got the 5 class members drawn out here. How many different ways can we choose 3? Now, this example is subtly different to what we were looking at in the last example. Okay, so the last example, we were basically starting off with 5 people, and then we were picking 3 of them, but we were doing something with those 3. We were actually putting them into positions, okay? So we were putting them in different positions and we could distinguish between them. This case is slightly different because in this case, we're not actually putting these 3 people into an order. We are simply just choosing them, okay? So that's a really important point, and I'll say it again just to make sure we've got it. With the last example, we were starting off with a group and we were picking some of them out, but then we were putting the people that we picked out into an order, okay? So in other words, the order mattered, whether something came first, second or third, right? In this example, we don't care about the order. We start off with 5 people, we pick 3 of them, but then we don't do anything with those 3. We don't put them into an order. We just simply want to choose 3 of them. We want to kind of take them out, okay? So in this case, what we're going to do is start off with 5 people and we're going to pick 3 of them. So here we go. So these are all the different ways of picking 3. And you notice the way I've drawn them as well. It's very deliberate, okay? In each group, in each of these groups, you've got different members, okay? So in the first group, you've got a pink, a blue and a green. In the next group, you've got a pink, a blue and a red, okay? In the next group, you've got a pink, a red and a yellow, okay? So in other words, in each group, you have different members, okay? So every group is unique, okay? Every group is unique. Sure, it's fine to have the same members in 2 groups. So for example, first group and second group, they both have a pink and a blue member, but the third member is different. That's what I'm trying to get across. So in each group has 3 members which are different. So no group has the same members in, okay? Has the same 3 members in. Now my point is here, the way that I've drawn them, I've not drawn them in a line. I don't care about ordering the 3 members that I choose. I just care that I'm choosing them. Okay, so I don't care about the order in this case. So because order doesn't matter, it means that if I pick a pink, a blue and a black person, okay, then it doesn't matter what order they come in. So if I pick a pink, a blue and a black person, if the pink person comes first and the blue person comes second, the black person comes third, it doesn't matter whether the pink person comes first, the black person comes second, and the blue person comes third. It doesn't matter. All of these orderings which I've got on the screen would all be treated as the same because I don't care about what order I put these students in. I just care that I'm choosing them. I don't care about the order. I'm not putting them in any kind of order. So to me, all of these people would be treated as the same. Okay, so if I have all these 3 different people, the orders doesn't matter. So therefore I treat each of these 6 groups as exactly the same group. Okay, whereas if I was dealing with a permutation where order does matter, I would treat these as different groups. So these 6 groups, this group, this group, this group, this group, this group, and this group. For a permutation, those groups would all be treated differently because I care about what order those people are selected in. In this case, I don't care about the order they're selected in. All I care about is does the group have a pink person, a blue person, and a black person? If the answer is yes, regardless of what order they come in, I'm treating it as the same group. Okay, does that make sense? That's really important, okay? So in this case, because I know how many people I start off with, 5 people, and I'm picking 3 of them, so ordinarily I have 10p3, but in this case, I don't want the 3 factorial arrangements of this group here, because I want to treat these 6 arrangements as being exactly the same group. I don't want to distinguish between them. So in other words, I've overcounted by 3 factorial. Just think, why is it 3 factorial? Well, it's because there are 3 different members in each group, and I've got to think about the ways of arranging these 3 people in a group, because I don't care about the arrangements, I want to remove them, all right? So therefore, if order did matter, it would be 5p3, wouldn't it? It'd be 5 people that you're starting with, and you're picking 3 of them to put them in an arrangement. But in this case, I don't care about arrangement, okay? So if I have a pink person, a blue person, and a green person, I don't care about what order those 3 people come in. This cares about order. So therefore, I need to remove those 3 factorial arrangements, the 3 factorial ways of arranging those 3 people in a group, okay? So therefore, because order doesn't matter, all of these arrangements are the same, okay? They're treated as the same group. I need to remove the 3 factorial arrangements. So in order to remove with factorial stuff, I need to divide. We've just seen that. So I'm going to take 5p3 and I'm going to divide by the number of different ways of ordering my 3 people. I don't care about the order. Okay, so therefore I'm going to take my 5p3, the 5 factorial over the 5 minus 3 factorial, and divide by that 3 factorial. Okay, and that would be a brand new thing. We call that a 5c3. The C stands for a combination or a choice. Okay, in this case I'm choosing 3. I don't care about ordering 3. I don't care about permuting 3. Okay, so it's exactly the same kind of idea as a permutation, just the only difference is I'm removing all of the different ways of ordering the people that I choose. okay? So let's generalize it then. With a permutation, the arrangement or the order matters, okay? So it's all to do with arrangements and orders, and in which case I can calculate that by doing NPR. Remember, the N stands for the number of people I start off with. The R stands for the number of people that I'm picking. Okay, and this is the way I calculate it. It's the n factorial, that's the number of ways of arranging those that n group, but then I need to remove the number of arrangements of the things which I don't arrange, okay, which is going to be n minus r, because I'm picking r of them. Whereas a combination, very, very similar kind of idea, except I just divide the NPR by r factorial to correspond to the fact it's just a selection, it's just a choice. I don't care about order, so I need to remove all of the orderings from the permutations, okay? Now you notice there's some new notation here. Because combinations are used quite a lot, okay, you can use NCR, okay, that is fine. But the other way of writing it is like this. Now don't confuse this with a vector. So if you don't know what a vector is, we will meet it later on in the course. Do not confuse this with a vector. If you're dealing with it in probability, it means NCR, okay? So if you write it like this, it means you start off with n objects, and it just means you pick r of them. You don't put them in an order. Okay, and you can see the relationship between NPR and NCR. It's just simply you're dividing NPR by r factorial for a combination. So permutation means that there's an arrangement or an order implied. You're worrying about putting these people into a particular order. Okay, so if it's red first, blue second, then green last, that is the order which you're interested in, and it will be different arrangement from from black first, blue second, and pink last. Okay. Whereas a combination means you don't care about what order they come in. So all you care about is you're choosing a black person, a green person, and a blue person. Okay? All right, fine. Let's have a go at these questions here to finish off with then. So let's suppose, so this is my general formula up here. Let's suppose we have a test and it consists of 10 questions. Now, we must choose and answer only 6 questions. How many ways can the candidates answer the test? Now, in this case, we don't care about what order the candidates answer the questions. Notice the wording of the question. They just have to choose and answer 6 questions. We don't care what order they answer the questions in. So in that case, you're going to start off with 10 questions, okay, 10 questions, and then you're just simply going to choose 6 of them. So it's going to be 10, choose 6, okay? And the formula for that, well, it's going to be 10 factorial. That's the number of ways of arranging those 10 questions. Okay. And then it's going to be 10 minus 6 factorial to represent the 4 questions which you don't answer. How many different ways are there of arranging those? But because we don't care about the arrangement of the 6 questions either, which we've chosen, we're going to divide by another 6 factorial. So we're just simply using that formula in the top left-hand corner of the page. Okay. Now, handily enough, you could type this in a calculator, but handily enough, just next to where you find the P on your calculator, there will be a C. Okay, so in this case, just above the divide on my calculator. So I'm going to go 10, then I want C, in this case, 6. So 10C6, that's going to give me 210. Okay, it's going to give me 210. So there's 210 different ways of answering this question. Okay, so answering this test. Let's have a look at the next one. Okay, let's have a look at the next one. So 6 students are chosen to go on a school trip. There are 20 students in the class. How many different ways can this be chosen? Okay, so if there's 20 students to start off with, you just need to choose 6 of them to go on the school trip. So it's going to be 20 choose 6. If I stick that on my calculator, okay, in this case, it is going to be 38,760. So there's 38,760 ways of choosing your 6 students from a group of 20 to go on a school trip. Now the last one I'm not actually going to go through now. Instead, I'm going to go through it I'm going to ask you to go through this as part of the weekly task. So in this question here, there are 8 men, 10 women in a group. A committee needs 5 men and 6 women. In how many ways can the committee be formed? I'm going to ask you to go through that as part of the weekly task. Okay, so please can you answer that and upload the weekly task to Flipgrid, same as usual. So that question 3 on slide 29 of theme 2. Can you have a go at answering that for homework? Okay. Okay, fine. So just to finish off then, let's have a look at just doing a quick summary of exactly what we've learned today. So this is pretty much it with regards to counting and ordering objects. Okay, so first things first, what do we look at? Well, we looked at n factorial. Okay, and we said that n factorial was simply the number of different ways of arranging n objects into a line. Okay, so it's the number of different ways of arranging n objects. So for example, if you had 5 objects, the number of ways of arranging those 5 objects would be 5 factorial. If you had 10 objects, the number of ways of arranging those 10 objects would be 10 factorial. Okay, so this is if we want to arrange every single object that we have in front of us. And we looked at sort of some conditions. For example, what happens if you want these 2 objects to always be together? Or what happens if you had repeated objects? Okay, if you had repeated objects, you just need to divide by the number of different ways of arranging those repeated objects. You need to remove them from your factorial. Then we looked at the idea of not arranging all of the objects in a line, only arranging some of them, okay? And this was NPR, okay? So this was basically the idea, the way which we calculated it was n factorial over n minus r factorial, okay? This idea was, it's the number of ways of arranging r objects from a group of n. Okay, so if you start off with n objects, okay, if you start off with n objects and you only want to arrange some of them, so you only want to arrange r of those objects, that's how to work out the number of different ways of doing that, okay? And it's just simply all of the objects arranged, and then you remove the objects that you don't arrange, okay? So the number of ways of arranging the objects that you don't arrange, okay? And then finally, we looked at this thing, which is NCR. Couple of different notations. You could either write NCR or you could write it like a vector, like this. And the way to calculate it was n factorial divided by n minus r factorial. But then you just divide by another r factorial. So it's basically NPR, this thing up here, divided by the number of different ways of arranging the objects that you're selecting. Because in this case, it's not the number of ways of arranging the objects, it's the number of ways of choosing r objects from a group of n. Okay, so it's the number of ways of choosing r objects from a group of n. So it's really important to understand the distinction between a permutation. The permutation is to do with arranging objects. Okay, so you're literally taking your objects and you're putting them in a line. Okay, you're arranging them. Whereas a combination, you're not worrying about what order they come in. Okay, so you're just worrying about just selecting these objects, but you're not actually putting them into an order at all. You're just simply taking these objects and you're just keeping them for yourself. You don't care. So for you, whether it comes red, blue, green, it doesn't matter where it goes, red, blue, green, or green, blue, red, or blue, red, green. It doesn't matter what order they come in, you treat them as the same group because you just worry about selecting them, okay? So it's important to understand the distinction between a permutation and combination. It all stems from the idea of a factorial. It's the number of ways of arranging n objects. The NPR is what happens if you don't want to arrange all of those n objects. And the NCR is what happens if you don't want to arrange the objects that you choose. Okay? So in that case, there's NPR, NCR, and n factorial. So that's what we've learned today, the number of different ways of arranging those objects. Now remember that this is really important because it comes back to this idea of probability. Just remember, I wrote it right at the very beginning, the number of different ways of arranging or working out the probability of something. You need to know the number of different ways or the number of different ways of working out an outcome, the number of different ways that something can happen. Okay, so for example, if you have a line for a photograph, okay, and you want to ensure that all of the girls will remain together, you want to work out what is the probability that you will have all of the girls standing together. You could use your permutations and combinations, your ordering and counting objects, to work that out, because you now have techniques to be able to work out the number of different ways of working out a particular outcome, number of different ways an outcome can happen. Okay, so just remember, this is kind of the key principles here. Key principles here. Okay. Now please remember to do that weekly task. Okay, so the weekly task, remember, was this. Okay, so it's question 3 on slide 29. So there are 8 men, 10 women in a group. Committee needs to be formed of 5 men and 6 women. How many different ways can the committee be formed? Please have a go at those questions for me. Okay, and that's to be uploaded to Flipgrid. Okay, but if not, we'll finish off there.